Alright, so the simulation has finished. We're looking at that. The goals took a little while to finish, approximately almost 8 minutes. Took 348 iterations. I believe that because the goal was invalid here, it might have stopped sooner if we gave it an obtainable goal to reach, but it just kind of it basically went until it reached its static pressure goal, I think. And then I gave a warning about vortex crossing the pressure opening. And so it gives you some comment here that has to do with the environmental pressure at the inlet. So anyway, there's things that you can play around with to try to get rid of these goals. Doesn't necessarily mean that the results are invalid, but it's just something to look at, definitely. See if we can just minimize or get rid of these goals, these errors. But we did the solver was able to converge, and let's go take a look at the results. And here's the geometry. And so I went ahead and let's look at this now. So we're going to show the flow trajectory. It's pretty much the same. So I actually changed instead of giving us pressure, I asked it to give us the temperature of the fluid. And so right away we know that this is in Celsius. We're not anywhere near where we want to be. So we want the temperature of the fluid at its hottest point to reach. So all the fluid, we want it to reach 100, and this one reaches 21. So it comes in as I think the initial condition somewhere is 20 degrees, and it basically heats up by maybe by 1.5 degrees. So this is not a good thing, right? This is not what we want to do. We want to get to 100. And this was just the first take, putting 10 watts at each thermoelectric cooler. Now let's look at the cool down. But so actually, then it should cool down, and does cool down. The air does cool down, but it cools down to basically almost pretty much the initial condition of 20 degrees. So it heats up by 1.5 degrees, and then it cools back down, which is what we would expect because we're putting 10 watts of heating and then we're removing 10 watts at the bottom. So now if we look at the temperature of the heat sinks, just see, sometimes you want to validate the simulation. To do that, you got to look at all the see if it makes sense. And so let's go in and look at the temperature of these heat sinks. For that, I have to go to surface plot, insert surface plot, and then I have to select the faces of these sinks. I can select the whole heat sink, but I'm just interested in these faces should be the maximums, and then I'm going to select where it should be the minimums. It's kind of hard to see here, but I'm going to select the bottoms of the other heat sinks there, and I want to see contour plots, and I hit OK. And what it does, it's a little bit hard to see, but it's linked. So the temperature of the fluid is these streamlines, and this is the temperature of the sink. So I'm gonna hide. So the temperature of the sink only really reaches 21.1. If you remember, the air was 21.4. Actually, this is the temperature of the fluid. So these temperatures here are warmer. Let me just hide hold on a second. Hide the streamlines, and I want to select. Let's give me the temperature of the fluid. I want to see the temperature of the solid. Okay, let's see if that changes. So no, that is the temperature of the solid. So the solid is only reaching around 21.2 or so. Here it's at its hottest. It makes sense because as the air is getting warmer and warmer, the surface, those 10 watts basically provide more heat there. And let's look at the bottom now. Now this is good. This shows that this is working as a sink. It's actually going below 19.3, but not that much below. And then it's coolest here, and then it begins to gradually. Anyway, so the model looks like it is behaving, but where we want to get is nowhere near. So what I would want to do is increase at least by the factor of 10 the power needed at these heat sinks, and I'll do that. It's going to take a while to run, but this is basically the gist of the simulation tool. Again, going back and dealing with the warnings is probably prudent to make sure you're looking at what you're seeing is correct. Though I have confidence that we did reach a convergence in a steady state. So I mean I have solid reason to believe that we're at least the model's telling us what we want to see. So if I was going to look at the flow trajectories again, and you can see some interesting things here. I'll hide the, you can see how there's some vortices here developing. It's not too many. If I increased the amount of streamlines, I might be able to see more. I mentioned about some vortices at the exit, at the pressure exit. I don't see any here, so I don't know what they're talking about. But again, we only have about 40 streamlines, 30 to 40 streamlines. Maybe I increased that. You can see the vortices don't tell you anything. I mean, it just tells you that they'll probably experience more back pressure. There's another one here. There's kind of an abrupt. Actually, it's not a vortice either. But this is the gist of the tool. Next, what I would do is just add more power to the heat sinks and more cooling. Maybe you might have to add more cooling add more power to the heat source, more cooling to the heat sinks, and see what you get. And obviously, if you have to come up with 1,000 watts to be able to heat up the air and then 1,000 watts to remove, that doesn't really make a lot of sense for portability. There's things you can, again, this is just a concept. Other things I can do is maybe there isn't enough back pressure here to slow the air down so that we can heat it up. Maybe I could put more restrictions here, maybe some screens or something like to help restrict the air and slow it down so we can heat it up. To me, what it's looking like might be look good to see if there's a function here. It gives us a heat sink efficiency. It tells us that basically we're just blowing past these heat sinks. The other thing is 10 watts doesn't seem like a good enough. I mean, this temperature of this bottom heat sink just barely reaches 2 degrees above ambient temperature, so that's not good either. All right, so this is basically the tool. Thank you.